This is Lab 2, Motion of a Falling Object by Connor Logan. The purpose of this lab is to compare the observed motion of a falling object, and crucially a falling object with some non-negligible amount of drag, to several computational models that are attempting to replicate this motion. And the result of this lab is that a computational model where drag is proportional to velocity squared is pretty accurate to the observations we see in the real world. So some important physics principles to think about in this lab. As always, Newton's second law, probably most conveniently written in the mass times acceleration form for this lab. This is important because this writing of Newton's second law makes it very apparent where we get terminal velocity from. That is, when F net equals 0, there will be 0 acceleration. So our object will fall at a constant velocity. And F net equals 0 when the two forces at play in this lab cancel each other out. That would be the force of drag, which is equal to some constant in the proportionality times velocity squared. And the direction for this vector is just opposite the direction of motion. And then, of course, the force of gravity, which is just, as always, mass times g. So, for our observed motion, we used a tracker and a video recorded at 30 frames per second. The travel distance was 1.24 meters. This was measured out with a ruler in my room, and the time for the object to fall was 1.5 seconds. In this case, the object, which is just a little bag, would be our system, and the surroundings for our system that are applying forces would be the Earth, applying the force of gravity, and the atmosphere or air in my room applying the force of drag. For our first computational model to try and model this motion, we didn't have any drag. We did have some constants that we set, as we can see on the left. There's the mass, which was just massed from the bag. We have the initial time, which is just taken from tracker. We left out the first couple of frames just because my hand was still applying some force to the bag, most likely. We also had this initial position, which was 0.009 meters. This was just because where we set the axis in tracker was slightly below where the bag was in the first frame. So just to get everything to line up nice, we had to set an initial position. Delta t was set to 1/30th of a second because we were recording in 30 FPS. And then g is just our standard 9.8. And the proportionality constant was set to 0 because we didn't want any force of drag in this model. And then on the left, we can see the forces we were talking about when we were talking about Newton's second law before. But only the force of drag is actually getting applied here because the proportionality constant b is 0. And then below that, we can see the momentum principle being used to get our velocity update and our position update formulas. Our computational model with drag was very similar. On the left, the only real difference is that the proportionality constant is now 0.21. This was found just through trial and error to see what got it to line up with our movement from tracker. And this means that our net force on the right actually does have the force of drag now. So again, with Newton's second law, if the force of gravity and the force of drag are equal and in opposite directions, we won't have any acceleration. And the result of this is that we get a terminal velocity. You can see the slope becomes constant at some point for both the experimental and the computational with drag. We can also see that the computational without drag is vastly different than what we observed, whereas the computational with drag is pretty close. There is a little bit of an error in the middle of the data especially, and this is most likely because the BV squared model for drag is assuming a sphere, and I was dropping a rectangle-shaped object, and also there could have just been some drafts of air in my room. About terminal velocity, this is just the point where F net equals 0 for a falling object. That is to say, the force of drag, because of the velocity increasing, eventually equals the force of gravity, and the object will start to fall at a constant speed. This constant speed was negative 1.5 meters per second in our model with drag, but on the left in our model without drag, we can see that the object just continues to accelerate. Also, for the question of what if we threw the object down, we had some initial velocity towards the ground. If this initial velocity was greater than our terminal velocity, we would still sort of reach our terminal velocity exponentially, or not exponentially, but in this curve. We would just approach it from the bottom instead of from the top. All right. That's been Lab 2. Thank you for your time. See you around.